Welcome to Lecture 15. We are going to continue our discussion about matter, as we have for this entire semester, really, but certainly in Exam 3 material, we are talking about how matter interacts. We started off this material talking about mixtures. Mixtures then may be turned into chemical reactions if new bonds were made and bonds were broken. We are going to talk about mixtures some more because we are going to now be a little bit more realistic about how most chemistry is done. We just finished our discussion about stoichiometry, and in review, if I take a balanced chemical reaction, I can get amounts of any of these substances as long as I know the amount of one. And of course, those amounts can only be compared in moles. So your first step is to get into moles if you are given an amount in grams. And then you can compare, you can go to C, you can go to D, you can go back to A. Doesn't matter which direction you go in, you're going to use the mole ratio. If I go to C, then it's 3/2 from B, and so on. Well, in doing these, and there it is like a box. In doing these types of problems, we have essentially been indicating that you are going to weigh out grams and you're going to end up with grams. Well, that is possible and certainly applicable in some cases, but many chemical reactions are done in solution, and where you take a bottle of something off the shelf and it's dissolved in water, and you take another bottle of a different stuff off the shelf and it's dissolved in water, and you have a little dropper and so on, and you mix these things together. Well, we need to talk about what solutions are, how to quantify them, and that is when I say quantify, I'm talking about the concentration. And then, of course, by the end of this material in Lecture 16, we will come back to, once we know how to count, we will come back to stoichiometry using solutions. So that's kind of the picture of where we've just been and where we're going. At the beginning of Exam 3 material, we talked about homogeneous mixtures and that they are so well mixed that you can, that they look like one thing. Solutions are generally a special type of homogeneous mixtures that you can see through. So it doesn't mean that they're colorless, it just means that they're clear, with the exception of solid-solid mixtures like alloys of metals and so on. Most chemists would refer to alloys as a homogeneous mixture. In fact, if you look back at that chart at the beginning of Exam 3 material, I believe alloys are actually placed in a separate category. Anyway, let's talk about one solution that we are familiar with on a day-to-day basis, but you may not be aware of it, and we'll bring in these terms solute and solvent. The type of solution that you are most familiar with is, let's say you want to make some pasta at home, some spaghetti, and you get a pot and you put some water in it, and generally you put a little bit of salt. Okay, and the salt dissolves in the water. Well, one reason that you do that is because it makes the food taste better, but it also raises the boiling point. But that's not what we're really after to talk about today. So this is the type of solution that you're familiar with. Also, making Kool-Aid, we talked about that, and so on, where you dissolve a solid in a liquid. Obviously, the substance that is there in the greater amount, larger amount, is the solvent. So water is your solvent most of the time. All right, the solute is what you put in to the water, so it's there in the smaller amount. One solution that you may not be thinking about is air. What is the gas that is in the largest component in air? It's nitrogen. It's like 70% nitrogen. So nitrogen would be the solvent, and all of the other gases that are there in smaller amounts, oxygen, carbon dioxide, a little bit of helium, there's lots of trace gases, those would all be solutes. It's a solution, you can see through it, looks like one thing, doesn't look like anything because it's a gas, a colorless gas. All right, so solutes are the substances that are present in the smaller amount when you mix two things together, and the solvent is the substance that's there in the larger amount. All right, I'm going to scroll and get rid of the pesky Adobe Updater down here at the bottom because it's driving me crazy. All right. Now, there are things we can talk about how much solute will dissolve in a solvent, and that is called solubility. Okay, how much solute will dissolve certainly depends on the solute and the solvent, and it depends on temperature. All right, we are not going to do anything quantitatively with solubility. You can actually relate it to what we're going to talk about today. Usually it's in grams per gram. That's over here on the y-axis of this graph. So I'll just wait till we scroll to talk about how solubility is expressed. But this graph is about how solubility of most ionic substances varies with temperature in water. All right, so there's our solubility right there. Grams of the salt, remember we call all ionic compounds salts, in 100 grams of water. So that's how a solubility is generally expressed. And as you can see from this graph, most of the substances, not all, here's an exception right here, the cerium sulfate, decreases with increasing temperature. The one you're most familiar with, table salt, actually does increase with increasing temperature, but not greatly. But almost all the rest, pretty much increase considerably with increasing temperature. The amount that will dissolve increases with increasing temperature. There is a problem in our practice and in your recitation about how to determine how to look at one of these graphs. And I think there's also one on sapling. So let's talk about that real quick. If I am talking about potassium nitrate, okay, at 20 degrees, at 20 degrees, the temperature's down here at the bottom. At 20 degrees, we go up to our potassium nitrate. 30 grams of potassium nitrate dissolves in 100 grams of water. At 70 degrees, it's probably a little too high. Let's go to 50. At 50 degrees Celsius, go back up to the same graph. Okay, here it is, intersects right here. And if we go over, looks about 87. So we go from 20 grams in 100 to 87 grams in 100 when I go from 20 degrees Celsius to 50 degrees Celsius. Okay. Now, I know one problem in sapling, and I don't want to, muddy the waters here by talking about it. They have you looking at one of these graphs, but I'll just kind of give you the idea, and then we'll talk about it in recitation. They tell you that 20 grams dissolves in 50 grams of water, and then they give you the graph and ask you how much dissolves, something along these lines, how much dissolves at, and let's say this is at 20 degrees, how much dissolves at 50 degrees? Well, you can't compare this to what is on the graph because they're in different units. This is in 100 grams, this is in 50 grams. So the first thing you have to do is set up a direct proportion, and that's, Sapling asked a question like that about this graph. So just giving you a heads up, we'll talk about it when that comes up in recitation. All right, so increasing temperature. I always tell students about making rock candy. I don't know if you've ever done that, but I did it one time with a 9th grade class, and it was really disgusting. They did not want to eat it after we'd made it. You know that sugar dissolves quite well in water. And since you have grown up in sweet tea country, you know that as you raise the temperature of the water, more sugar dissolves. And many people take advantage of that to get the tea even sweeter. So, to make rock candy, what you do is you take like boiling water, okay, and you keep putting the sugar in until you can't get any more to dissolve. And then you let it cool. So you're essentially, if this were sugar, if this were sucrose instead of potassium dichromate, you can get this much in at a high temperature, but only this much in at a lower temperature. So the difference between the solubilities, and if you let it sit there and let it slowly crystallize out, that difference of roughly 82 grams to about 5 grams comes out as little rock crystals. And that's how rock candy is made, but it's a disgusting amount of sugar. Okay, solubility increases with increasing temperature. An exception to this is gas solubility in water. Gases actually tend to decrease in solubility with increasing temperature. And this is why lakes become starved for oxygen in the summer. The reason for this is that gases are generally nonpolar and do not dissolve well in water anyway. So with increasing temperature, the particles all move faster, and the interaction between the water, which is the solvent, and the solute weakens, so less of it dissolves. And I have a graph for that. And here it is. Now for oxygen, you don't see a huge decrease, but I'd like to see this portion of the graph blown up a little bit more so we can actually see the difference between here and here. But it is certainly very dramatic for carbon dioxide, which is nonpolar, so is oxygen. So as temperature increases, solubility in the water actually decreases for gases. So it goes against the solids trend. Now, if you were to change to a different solvent, a more nonpolar solvent, okay, like is shown here, then you see the kinds of increases in solubility with temperature like you do for the solids. The quick and easy explanation is that the organic solvents are more nonpolar and the gases are more nonpolar. So it behaves more like putting ionic things, which are the ultimate polar, in polar water. So, but that's the quick and easy explanation. I have reproduced here the explanation from the website where I got the graph, and it's pretty complex, but I thought that maybe some of you would like to see where you're headed by about Chem 132. A synthesized conclusion is that it's stronger attractions between a solvent and solute. That would be true. Stronger attractions between nonpolar and nonpolar. Gases are nonpolar. The organic solvents are mainly nonpolar. And entropy contribute to should be a greater transfer of heat or enthalpy. Thus, increasing the temperature of the solution will favor blah, blah, blah. So that's the more advanced explanation, but you do see that reversal of the trend when you switch to a solvent that is more like the solute. So that brings us to the universal way of looking at making solutions or dissolving things, and that is like dissolves like. So ionic things, which have charges, like to dissolve in or mix with, because dissolving something is mixing. It's not really a chemical change. Ionic substances are like water, so because they have charges, so they dissolve. Gases are not like water, so they don't dissolve as well, but if you switch the gas into a more nonpolar solvent, then they will dissolve better. And you'll see that increase in temperature dependence. Now, one thing else to talk about is what happens with gas solubility with pressure. So we exploit this, hence called Henry's law, that gas solubility increases in a liquid with increasing pressure. So when the cap is on the carbonated beverage, it is like this diagram over here. You have the pressure inside the bottle is higher than the pressure outside the bottle. So P1 is greater than P2. And the reason that they do that is because you can get more gas to dissolve in the solvent by increasing the pressure. And it has to do with equilibrium. At a lower pressure, less gas will dissolve. So when you open the cap, the sound you're hearing is that this extra pressure, the P1, is being released because now after the cap is opened, then P1 is equal to P2. So this is cap open and this is cap closed. So Henry's law says that gas solubility increases with increasing pressure. All right, now let's talk about a little bit more detail about what happens when things dissolve. Well, there's three things that can happen when compounds are dissolved in water. And it would pretty much have to be a compound to talk about what we're talking about. Three things that can happen are: one, nothing. Nothing happens to the particle, okay? We would call those substances non-electrolytes. Now the term electrolyte, you know, you've heard it in terms of like Gatorade and things like that, okay? Well, they contain electrolytes. So what does this word electrolyte indicate to you? It says to me electricity, charges. Well, if nothing happens to the solute particle, then it was probably, it was a non-electrolyte, and therefore it must be molecular, okay? Which means it's sugar or carbon dioxide or any other iodine or any other molecular substance, okay, that's non-metal. They don't produce charges, okay? So non-electrolytes, no charges. Electrolytes are all ionic compounds, are going to produce ions, and will therefore conduct electricity. The action of the polar water molecule breaks down an ionic crystal. I've shown you that simulation, where each ion, both the cation and the anion, becomes surrounded by water molecules. This process is called hydration. So that's surrounding the ion with a bunch of little water molecules. Oh, and I did it just the way it should have been done, and I wasn't even thinking about it. If that's a positive ion, it's the negative end of the water molecule, which is where the oxygen is. I've just been drawing these things for too long. Anyway, this is called hydration, and I've shown that simulation to you, I think, twice. All right, substances that do not produce ions, so the nothing, is non-electrolytes. This hydration of ions comes from electrolytes because you have produced electrically charged particles. All right. Now, when it's in the crystal, when the ionic compound is in the crystal, the positives and negatives cancel each other out, so you technically don't have charges. And that's how the whole basis of how we put those ionic compounds together. All right, so ionic compounds are electrolytes. Some highly polar compounds, molecular compounds, are just polar enough, and they also produce charged particles. All right. So now we need to talk about, so we've talked about the difference between non-electrolytes and electrolytes. And now we're going to make a distinction between how many charged particles you get. All right, so let's talk about these strong acids and strong bases. Well, strong bases are ionic compounds to begin with. Okay, so strong bases are ionic, therefore, so when they dissolve, it's like putting salt in water. You produce ions, and this is called dissociation. And they are definitely, they are strong electrolytes. Okay? Strong acids, on the other hand, are generally non-metal. And so there were no ions there before. Now there was a polar bond there, And the interaction of the water molecule with the HCl molecule produces ions where there weren't any before. So that's called ionization. It is different from dissociation in that the name ionization implies the creation of ions, whereas dissociation is they just dissociated. Here we ionized a molecular compound. Now, let's answer this question right here. How many particles are generated when HCl breaks up into now two ions? Well, two. This idea of one particle becoming two is very important, and I want to stress that by talking about these three substances right here: potassium nitrate, magnesium chloride, and sodium acetate. Because this idea of we're going by the end of this lecture, we are going to be quantifying the numbers of particles in a solution. So we have to understand that when I dissolve something, how many particles do I get? Because that is going to affect the amount of particles. So potassium nitrate, how many particles do I get when that breaks up? Think ionic equation. You get a K and you get a nitrate. So you have two, just like with the HCl. Magnesium chloride. When magnesium chloride breaks up into its ions, you get 3 particles of magnesium and 2 chlorine. When sodium acetate breaks up, you get a sodium, and then that acetate, which is molecular, really, all nonmetals, is just one big particle. So you get 2 ions. Okay, we will return to this idea a couple more times because it is an important idea. When you break things up, especially making these solutions, how many particles do you get? All right. So, strong versus weak electrolytes. We've talked about the difference between electrolytes and non-electrolytes. Now, what is the difference between strong and weak? I've already talked about strong acids and bases being strong electrolytes, but what does it mean? There are differences in the amount of electricity that different solutes dissolved in water can produce. In fact, I'm going to show you a little simulation online about that. There may be 2 things going on here. First of all, as we observed, even tap water has enough electrolytes in it to conduct electricity, so we know not to stand in the bathtub filled with water when you dry your hair with an electric dryer. So, tap water either has a low concentration of strong electrolytes or it has a weak electrolyte. Some molecular compounds do not completely ionize. All right, so HCl, like we mentioned before, strong acid is a strong electrolyte. And what that means is before HCl was dissolved, there was a red, I'm assuming it doesn't matter which one it is, but these 2 particles were HCl, were together. After it dissolves in water and it ionizes, every single one of these HCl molecules breaks apart. That is what a strong electrolyte is. Strong electrolyte is every dissolved particle is ionized or dissociated. Okay. On the other hand, weak electrolytes like these pictured here, the weak acid carbonic acid, and how do you know? Because you've memorized your strong acids, everything else is weak. Here it gives you a little key. The majority of the particles in this beaker are the undissociated acid, or the unionized acid is what it really should say. And then your black circles are the H pluses, and the free anion is your blue in the case of the hydrogen carbonate ion, or I guess it was red up here for the HCl. But anyway, up here, every single particle ionizes or dissociates. Only a few dissolved particles are ionized or dissociated. And that's what a weak electrolyte is. So you will find out in maybe 131, but you will look at it in detail in 132, is the difference in the chemical equations for weak is that it involves both a backwards and a forwards reaction. Because HF molecule, few of them are producing the ions, but then just as likely, these ions go back to being HF. Now, when you write these acid equations, and we will look at this more in exam 4 material, H plus doesn't really exist by itself, so we hook it onto a water molecule, but the take-home message is if you're going to write an equation for a weak electrolyte, you use the double-sided arrow. Strong electrolytes, every single one of them becomes the products. So if I am dissolving, let's pick a different one to talk about. Let's talk about aluminum sulfate. All right, it dissolves, so it's a strong electrolyte. Well, I call all ionic compounds strong electrolytes because even the ones that do not dissolve, well, if the few particles that do dissolve, they're all broken apart. Okay, but anyway, this one dissolves quite well, and when it dissolves, you know, if we wrote this in its ionic form, this is what we would write. So when one aluminum sulfate breaks apart, you produce 5 ions. Okay, and I use the single one, arrow that points to the right, meaning that all of the aluminum sulfates become aluminum and sulfate. That is not true for weak electrolytes. Only a few of them do, so we use the double-sided arrow, which implies an equilibrium system, and you will study that in detail in 132. Okay, to summarize. Strong and weak electrolytes differ in the degree of ionization, but concentrated and dilute solutions, which we haven't really talked about that a lot yet, differ in the amount of dissolved solute. All right, so I'm going to do 4 different pictures here. All right, first of all, I'm going to do a strong electrolyte that is concentrated. Okay, so this is going to be strong, and over here we're going to have weak. Okay, this first one, and I'm going to make it simple, just a little 2-particle system. Every single particle, where before I dissolved it, it looked like this, so it could be HCl. Every single particle breaks apart. And there's lots of particles in this one because this big one in there is this is a concentrated. So this is a concentrated, meaning I have lots of solute of a strong electrolyte. Here is a strong electrolyte. Every particle is still broken apart, but it's not as concentrated, so we call it dilute. Okay? Over here, weak electrolyte, that is concentrated. So I'm going to use the same type of picture, but the majority of my particles are going to stay together because this is a weak electrolyte and only a few will break apart. Let's do another couple. And this is the concentrated one, so I have lots of solute. Okay? So this is a concentrated weak electrolyte. All right? A dilute weak electrolyte would just be fewer particles altogether. And this would be a dilute. So you see the difference between them. What we have left to do is quantify this concentrated versus dilute. Okay? So, in summary, strong electrolytes are all ionic compounds and strong acids and bases. Weak electrolytes are polar molecular compounds, and which include weak acids and bases. Non-electrolytes are nonpolar molecular. Now they can be polar, I would say that it's molecular compounds and some, because sugar is polar, but it doesn't break apart, and some polar molecular compounds. It's just not polar enough like HCl is to be taken apart by the interaction with the water molecules. Okay? All right, one more thing to do, and this is where the calculator comes in. Concentration, strong versus dilute, represents the amount of solute dissolved. We can do it as a mass percentage, where you take the grams of solute over the grams of solution. So again, like any other percentage, it's the part over the total. So you'd be taking the amount of solute plus the amount of solvent times 100. And then the other one that we're going to use is molarity. And look, it starts off with the word mole. It's the big M, and it is defined as the moles of solute over liters of solution. And this is the one we're going to use. And in fact, we can put it on our mole chart. Now, I have included one more thing on the mole chart that we haven't talked about yet. Well, it's coming later, but I wanted to give you a completed mole chart with all the things. Now, we talked about this way back at the beginning. Avogadro's number to go between moles and particles. To go between mass and moles, molar mass from the periodic table. Okay? Now, I can use molarity to go back and forth between moles. Because you know when I start to do stoichiometry in the next lecture and I'm using concentration, then I need to be able to get to moles because if you're not moles, get there. So when I have a molarity and I want to get to moles, I multiply times the volume in liters. To get a molarity, you take the moles of solute and you divide by the liters of solution. And we will talk about this fourth one in exam 4 material, right at the end of the course. So before we do some practice problems, let's look at this simulation that shows you how electricity is conducted based upon whether the substance is strong or weak and also concentration. Okay, so let's see. Let me get this where you can see it a little bit better. There we go. I want to be able to get to this other side. All right, well, we'll do some acids, and then I don't know if we can get over to the bases. That's weird. All right, well, let's do some acids. All right, excuse me. Oh, I know how you do it. Okay, so HCl, strong acid, and let's do, I really wish they did the similarity, but they don't. We'll do 10 grams. Well, let's see, it's times 10 to the minus 1. So let's, if we want to do 10 grams, we'll do 120 milliliters. And then we're going to press connect. Okay? And you see this little green bar right here? Well, let me get my little pen working. Here we go. See this little green bar right here? Right here. Keep your eye on that, okay? Because I'm going to increase the concentration. All right? So let's make it, oops. So let's make it 1,000 in 20 milliliters of water. Ah. Oh, look, I can use this. Maybe not. So let's do 20. We did 200. Oops, disconnect. Oh. We did 100 before, so that was the highest. And can I change this? Let me. All right, well, let's change it. Let's do disconnect. Okay. Let's do HF, which is a weak acid. And let's do 100 grams in 20 milliliters of water. Connect. Get the same reading as we did for the the HCl, sorry. Let's try this one more time. 100, connect. Same reading. Okay, well that doesn't help. Let's disconnect. You can also key in the value between 1 and 100 in the box. Oh, there we go. Okay. All right, it's letting me do the slider now. I guess I had to be disconnected. All right, let's connect that. Whoa, look at that. So I think I just had to have my little probes buried enough. So that's our strong acid. Yay! All right, let's disconnect and let's try the weak acid. Okay. Yeah. And let's do the same thing. Okay, not as much. All right. Now that wasn't the same. Let's see, can I? No, I can't. I gotta disconnect. All right, let's change it to the larger amount. I don't remember where we were before with the HCl, but let's connect. All right, so you definitely see a difference in the amount of conductivity between the strong acid and the weak acid. Okay, disconnect. Let's do something like, let's change to a salt. Okay, so sodium chloride is all of these. You see that it's sodiums in the front or ammoniums. So these are all quite soluble. We really shouldn't see a difference. Okay, ammonium nitrate. And let's do the bigger volume. Let's say connect. Okay. All right, so ammonium nitrate. Now that's a +1, -1. All right. Let's try sodium sulfate, which, how many particles are we going to get from sodium sulfate versus ammonium nitrate? So let's see if that makes a difference. I get 2 particles when I dissolve the ammonium nitrate. Okay. But I get 3 particles. It's letting me write on it. But I get 3 particles when I dissolve the sodium sulfate. So let's try that. Okay. All right. So let's switch it to sodium sulfate. Let's do I like the larger volumes. And let's say connect. Wow. See? More particles give us a higher amount of electricity being conducted. So that's another reason why it's important to understand the numbers of particles. Let's do ammonium sulfate. We should see something very similar because that's got 3 particles as well. 2 ammoniums and a sulfate. Increase our volume. Connect. Not as good. Wonder why. And then just one more time, let's compare it to just regular old table salt. Okay, some volume, connect. It's pretty good. All right, I'm sure it has to do with solubility as well. Okay, let's try bases. Let's try, I see some strong bases up here at the top, and then I see a whole bunch of weak bases. How do I know they're weak? Because they're not the strong ones I memorized. So sodium hydroxide, let's fill that beaker up about halfway, and let's say connect. Okay, lots of conductivity. Okay, and let's do one more, and then we're going to go back to our notes. Weak base. And this is bookmarked, so you can play with it if you'd like. Connect. Much less conductivity, it's a weak base. You don't have as many particles. All right, back to the notes. All right, some practice, and then we're finished. Number 1, identify the solute and solvent in each solution. So 80 proof vodka. Never understood why, when it says 80 proof, that it's half of that. It's 40%. So if it's 40% ethyl alcohol, what's the solute? The solute is the alcohol, and the solvent is the water. Okay? Oxygenated water. Water is the solvent, and oxygen is the solute, because it's there in the smaller amount. Antifreeze. Now, I can't remember what they sell. I think it's around 30% ethylene glycol. This is a fun set of solutions to work with. But anyway, 30% ethylene glycol, water is your solvent, and the ethylene glycol is your solute. What are the dissolved particles in a solution containing a molecular solute? Those would be molecules. The name for this kind of solution will be a non-electrolyte solution. Oops, sorry about that. All right, number 3, a potassium nitrate solution. So this is, we're going to have to go back to the graph. Okay, so remember that when Sapling asks you about cooling and solubility. All right, so we have 110 grams of potassium nitrate, and we're going to cool from 60 to 0. All right, so what I'm going to do is I will lose what I have written so far because I want to scroll up to that diagram. All right, so 110 grams, 60 to 0. There we go, potassium nitrate. That's the green line. All right, so we're going to go from 60 degrees centigrade right here to, I need to, there we go. And it's unfortunate that at 60 degrees centigrade right here, it doesn't even intersect the potassium nitrate line. But when you cool down to 0 degrees centigrade, you are going to go from, it was 100, I'm sorry, it was 110 grams in 100 grams of water. So I'm assuming that about at 110, that is the maximum solubility. So we're somewhere up here, and the curve, and the curve kept going like this. So we went from 110 grams in 100 grams of water to about 13. So 110 minus 13 is 98 grams of potassium nitrate would, this is how we would say it, would either precipitate, or another way to say it would be or come out of solution. So at 60 degrees Celsius, you can get 110 grams of potassium nitrate to dissolve, but you cool that same solution down to 0 degrees Celsius, then you can only get 13 grams to dissolve, so 98 grams would not dissolve and would come out of solution. Okay. Alrighty. I purposely did the lecture in the dining room so that you could hear the dog again. I know you've missed her. All right, number 4. A mass percentage. Like all other percentages, it is part over the whole. The part is the solute. And so this is in milligrams, and this is in grams, so I'm going to convert those milligrams to grams. 32 milligrams divided by 1,000. And so I've got 0.032 grams. So 0.032 grams over the total, which is the solute plus the solvent, times 100. All right. Calculator. So 0.032 divided by 309.032 and times 100, very small, and it is 0.01%. All right, calculate the molarity. Molarity, big M, is equal to moles of solute over liters of solution. Okay, solution, SOLN is an abbreviation for the word solution. So for the A, I'm going to take the moles of my solute, which is 1.54 moles, over the liters, which is 22.2. No conversions for this first one, being very nice. 0.069, 0.0694, or 6.94 times 10 to the minus 2, 6.94, drop a line here, times 10 to the minus 2 molar, big M. All right. B, I'm already in moles with my solute, so 0.101 moles over, I'm going to convert the 3,000 milliliters to liters. 3,000 milliliters times 1 liter has 1,000 mils, so that is 3 liters over 3 liters equals, all the animals going today, 3.37 times 10 to the minus 2. Excuse me. Excuse me. 3.37 times 10 to the minus 2 molar. All right? And then our C, now I have to convert to moles because I'm given my amount in grams. So 0.30 grams, 1 mole of glucose weighs, I'm going to add all those up. So 6 times 12 for carbon, so 72, plus 12.12 for the hydrogens, and 96 for the oxygens, and that should add up to 180. Yep, 180.12. All right, and that'll give me my moles of solute. Then I'll have to convert these milliliters to liters. And I get 1.67 times 10 to the minus 3 moles. And then my liters, 76.2, just as if I were to put that here, divided by 1,000 would give me 0.0762 liters. So that my molarity is 2.19 times 10 to the minus 2. Actually, I should do two significant figures, so 2.2 times 10 to the minus 2 molar. All right, number 6. Number 5, we were just finding molarity, moles divided by liters. If you go back up to the mole chart that we talked about earlier, if I'm going to go from molarity to moles to grams, okay, you can use the mole chart to do that. And that's fine. I am going to do it using dimensional analysis. So I always tell students that the first thing you want to do with molarity, especially, is rewrite the big M. So it is 0.210 moles over, I'm going to give myself more room. So if you need to get anything that I've already written down, go ahead and pause the video and get it. But I really do need some more room here. Okay. Okay, and then might as well go ahead and do the same thing for these other two. Okay. All right, so rewriting the Big M. It is 0.210 moles over liters. And now I want to use this volume I want to get to grams. So the first thing I want to get rid of is the liters. Well, I have that here. I'm going to go from liters to milliliters, 1 liter on top, so it cancels, 1,000 milliliters on the bottom, conversion factor, times the 355 milliliters, and now those cancel, right? And that'll get me moles. But I know how to go from moles to grams. Here's my formula. Potassium is 39.1 plus 14 for the nitrogen, plus 48 for the oxygens. 39.1 plus 14 plus 48. And I end up with 101.1 as my molar mass. So times, mole is on top, so it needs to be on the bottom. Grams on top, 101.1 grams per mole. Moles cancel, and I end up with my answer in grams. Now, let's dissect this in terms of the mole chart. You would have started at the bottom with molarity. You would have multiplied times the liters to get to moles. And then you would have multiplied times the molar mass to get to mass. So that's what we did. All right, but I did it using the units because that's the best way. All right, so 101.1 times 355 divided by 1,000 times 0.21. And I get 7.54 grams. So you're working in a lab and they tell you, oh, we need some 0.21 molar potassium nitrate. Let's make about 355 milliliters, which would be kind of silly. They'd probably say 400, but this is how you would calculate it. And I used to tell my advanced students when I was teaching high school that knowing how to do this will ensure that you don't have to wash dishes all the time. So you would take your 7.54 grams of potassium nitrate, you dissolve it in some water, not all the water, and then after it's dissolved, you take the volume up to the total volume because it's liters of solution. And the piece of equipment you would use, because a lot of the 131 instructors think you should know these things, is called not very symmetrical there, a volumetric flask. It has a little line on it. That's the most correct way of making a solution. All right, calculate the volume needed to make the following solution. So now we're being asked about volume. So I'm going to rewrite the Big M, and just like I've done before for other conversion factors, a molarity can be thought of as a conversion factor between molarity and moles, okay? I am going, because I want the part that's on the bottom, I am going to flip that molarity over. Okay? All right? Because I'm going for volume. Moles. All right? Containing 96 grams of magnesium nitrate. So, how do I get rid of moles and into grams? I use the molar mass. Okay? So, magnesium. So I'm doing this completely by the units, and this is where knowing how to do the dimensional analysis becomes really important when we're doing things like this that are not at all intuitive. So 24.31 for the magnesium, 28 for the 2 nitrogens, and 96 for the 6 oxygens. Okay? So 24.3 plus 28 plus 96. And we end up with 148.3 as your molar mass, grams per mole. So in this problem, I'm going to put the mole part on top. I'm going to put the 148.3 grams on the bottom. This gets rid of my moles. And now I need to get rid of the grams, and I'm going to use the grams given in the problem. And now when I do the math, I will end up with liters. Okay, so 96 divided by 148.3, which would get me to moles, and then divided by 0.4. And I end up with 1.62 liters. All right. B, same type of thing, trying to get a volume out of a molarity. So I'm going to take that big M and rewrite it, but put the liter part on top. Go ahead and stop at this point and give it a try, because this is just like A. All right. 1 mole on top to get out of that. And this is my molar mass right here, which I'm going to add up from the periodic table in a moment. And then I'll be multiplying times those 25 grams, and those cancel, and I end up with my liters. So potassium is 39.1, and chlorine is 35.45. So my molar mass is 74.55 grams per mole. So I'll put that right here. All right, so now I'm going to take the 25 divided by the 74.55, that's my moles, divided by 0.75. And my answer is 0.45 liters. Actually, I can carry that out to 3 significant figures, so 0.447 liters, or that is 447 milliliters. And that concludes lecture 15. Lecture 16, we're going to take this idea of concentration, molarity, and we're going to go back to stoichiometry, because I know it's your favorite subject. And then the quote-unquote 7th lecture is not new material, but it's going to be a whole page of practice problems that are at the end of the notes, and I'm going to walk you through those practice problems before your exam.